So we've talked about direct proportions. Let's talk about inverse proportions. Now, inverse proportions, if you think about inverse in math, inverse means opposite. Okay, so when we think about doing inverse proportions, it's kind of a unique relationship, but they don't come up too frequently, but they do come frequently enough that you need to be aware of it. So with an inverse proportion, as one amount increases, the other decreases. Okay, so some typical applications of this would be like the example I have right here, hours and speed. Naturally as speed increases, travel time should go down, right? It can't take you longer to get somewhere going faster, right? Another one would be like RPMs and diameter. You think as your diameter increases, your RPMs go down and vice versa, okay? Or pressure and volume, as pressure increases, volume goes down. I mean, there's just tons of examples. But let's kind of focus on the two examples I have here, okay? Because I think the problems I picked out here, I think these are two of the most practical examples for inverse proportions without getting too sciencey. Okay, so we look at this one. They say if a certain trip takes 2 hours at 55 miles per hour, how long will it take going 60 miles per hour? Okay, now again with this one, don't forget, proportions deal with ratios, and ratios are just a comparison. So what are we comparing in this case? Well, hours and miles per hour. Okay, so again, if you want to list the information off to the side, we got 2 hours, we got 55 miles per hour, and then we got 60 miles per hour. So they compared initially the 2 hours with the 55 miles per hour, so that's what goes together. Okay, so we're going to solve these. So these are almost the exact same thing as let me draw that a little better. These are almost the exact same thing as direct proportions, in that the first steps are the same. You find what goes together. Okay, so but in an inverse proportion, after you find the pair that's linked, you place them diagonal from each other. So if I put the 2 here, the 55's got to go here. Okay, now it doesn't matter how you place these. Okay, you could do 2 over here, 55 there, as long as the 2 and 55 are diagonal. So now the 60, it really doesn't matter where I put the 60, but I'm going to put it down here. Just because in my mind, I like having hours, miles per hour, hours, miles per hour. Then we got X right here. So let's cross multiply. So 2 times 55 gives me 110. X times 60 gives me 60x. Divide both sides by 60. Okay. And we divide that. Let's see, what does that give me? I think it's like 2.6 repeated or 2.3 repeated. Let's pull up our calculator here. Let's do 110 divided by 60. 1.83 repeated. Okay, I was way off. Okay, so now when you get a repeated answer like this, I would just round. I would say 1.8. If you want to be technical, like if I say round to the nearest hundredth, round to the nearest hundredth. But in this case, we're talking about hours, so let's just do 1.8. Let's be a little. Let's just ignore the repeating part. So we get about 1.8 hours. Okay, so now we look at this. This makes sense, okay? Because again, remember we're comparing hours and miles per hour. So as miles per hour went up, hours went down. Okay, so it fits our inverse proportion. They yo-yo. As one goes up, the other goes down. Okay, so that kind of fits. And you think about this logically. If I speed up, I should get there faster, not slower. Whereas if you flip these around, you would actually get there. It would take you longer to get there going at a faster speed, which doesn't make sense. But again, some people get in the mentality of just getting an answer to get an answer and don't really ask themselves, does that answer make sense? And in this case, 1.8 makes sense. Okay, let's go to the next example I have here. Oops. Let's see. Here we go. Here's another practical example of an inverse proportion. So they say if 5 workers can complete a job in 3 hours, how long will it take 2 workers to do the same job? Okay, so again, what we're comparing here, workers to hours. Okay, so let me see, I'm going to write this over here. 5, we got 5, 3, and then 2. So this is the hours. Okay, so in this case, we know the 5 goes with 3 because they said that many workers for that many hours of work. So if we place these in a proportion, now remember this is an inverse relationship, okay? Because think about it, if you decrease your workers from 5 to 2, your work time should go up. Should go up, okay? Let's see. So we put 5, and then the 3 has to go diagonal. Now remember, that's the difference between direct and inverse. Once you find your comparison, what goes together is they have to be diagonal from each other. Okay, so now with the 2, let's put the 2 up here because it's workers. Then we got x down here. So we do 5 times 3, which is 15. 2 times x, which is 2x. Divide both sides by 2. So we get x equals 7.5. Okay, in that case, it'll be 7.5 hours. And this makes sense because, again, we're comparing workers and hours. As the workers went down, the hours went up. Okay, so with inverse proportions, again, like everything in this module, it's a lot of rinse and repeat. It's a lot of more of the same stuff, I mean, a lot of this stuff is all hinged on getting the right information in the right spot. But once you get to here, it should be pretty easy going, okay? It's a pretty simple process. Okay, but the solving hasn't changed from day one, since we started doing the drill problems to now. But just remember, with an inverse proportion, after you find what goes together, they have to be diagonal from each other. That's the only way to ensure the number we get obeys what an inverse relationship should be. As one goes down, the other goes up, or vice versa.